In one of the last videos, I talked about understanding capacitors, and I think it's really important to understand what goes on the atomic level, because you get that intuition, you really understand what's happening. So it's really important to understand this for inductors as well. So let's say we have this wire, and we're passing a current through the wire from left to right. So the direction of the current is these arrows here. Then we know that what happens as this current gets applied is that we get this magnetic field line that appears perpendicular to the wire. So that's pretty simple. Now, what happens if we were to, and I'll just copy this and paste this here. What happens if we have half of the current? So let's say we decrease the amount of electricity flowing through this wire, we get half the current. What happens to this magnetic field lines? Well, they still exist, but they're a lot smaller. You know, we cut the current in half, we'll cut these magnetic field lines in half. And so this actually is the key concept to an inductor. So a changing current is a changing magnetic field. And that's the key thing here. If you can understand this, you can understand inductors. And so this might seem kind of boring, but really, even Einstein found this extremely interesting. He knew, and he mentioned this in his paper for general relativity, he knew that if you had this coil of wire, and you had this, let's say you have a magnet here, we've got the north terminal and the south terminal, then the magnetic field lines of the wire are going to look something like this. And he said, and he didn't come up with this, he was just talking about it, he said, if you move this magnet up and down in this coil, then you induce a current. And depending on the direction and the terminal that you're using, then you can get it in either direction. So he said that a changing magnetic field can actually induce the current. But then he's like, and this is why it was mentioned in his paper for relativity, he said you don't have to move the magnet up and down. You can just move the coil up and down and keep the magnet constant. So it doesn't matter if you move the magnet or if you move the coil, as long as that there's a change in magnetic field, as long as this coil sees a difference in magnetic field, it will have an induced current. So the coil might pass through here and it will see a different magnetic field than if it passes through here. And that change, so a change in magnetic field can induce a current in another loop. Now, if we were just to move this magnet down, so if we just took this magnet and we just stuck it here and we didn't move it at all, we're not going to get that induced current. It has to be a change in the magnetic field. That's the key thing. We can't just have a magnet sitting there. Otherwise, we'd have free energy. We'd just have a bunch of magnets sitting in a bunch of generators, not doing anything. We could play Xbox with those. Now, this is how inductors work. So this seems a bit abstract. Now let's consider a circuit. So we have our positive and negative terminal. And now we know that if we apply current here, we're just going to get these magnetic field lines appearing, and they're not going to do much because once it sits here, I mean, there's a magnetic field, but nothing interesting is happening. So let's consider another circuit. And in this one, we're going to put a small loop in it. So it's going to go loop around, and then it's going to come back. Positive and negative. And so what's going to happen here is we're going to have these magnetic field lines appear as soon as we turn on the current. But here, at this loop part, that's where it gets interesting, because these magnetic field lines will intersect with the other wire. And so we saw up here that if there's a changing magnetic field, it will induce a current. So what happens here is that if we were to, let's say, turn on the current, then in a wire, the magnetic field lines look like this. So this will be like for the first nanosecond, the magnetic field lines will be here, and if we gradually increase it, then the magnetic field lines, get bigger and bigger. So what happens is, if we were to gradually decrease the current in the circuit, then this will induce a current. And so I'll zoom in on this loop. So we have this loop here, and we have our magnetic field lines. So the first second, we're going to get these magnetic field lines of getting bigger and bigger, and then eventually it will intersect with another wire. So I can get rid of these now here. So at full current, you can see this line's magnetic field intersects with this one. And so what happens is that when we reduce the current, look what happens. We get the magnetic field line gets smaller and smaller, and when it gets smaller, it's changing, and when it changes and it passes through this wire, it will induce a current. So just as here, we saw that the only thing that matters is this changing magnetic field, and that will induce a current. So we have current flowing this way. When we reduce the amount of current, it's going to induce a voltage. So this is of course this direction and this direction for the current. And when this magnetic field line gets reduced, it's going to make this, it's called a back EMF. And it's the counter electromotive force, because when this magnetic field line gets smaller and it changes, it will oppose it. So it's going to induce this current backwards. And so that's why inductors resist change in current. When the wire, let's say we go from 0 amps to 5 amps. The only time the magnetic field line is changing is when the current is going from 0 to 5. After 5, nothing happens, just as if we had that magnet just sitting there. But when it's increasing or when it's decreasing, we get these magnetic field lines that keep getting bigger and smaller. And when that happens, that's when an induced current appears. So let's take one more example. We have our circuit here, and let's put a couple more loops. We're going to have multiple loops. Actually, that's pretty terrible looking. Okay, I need to use a smaller pen. Fine, chisel. There we go. And then we have our current flowing back. Is it a positive, negative terminal? Now, we know our magnetic field lines are going to appear. And here you can see this is sort of what an inductor looks like, is that these magnetic field lines are all going to be crisscrossing each other. And so when we apply current, these magnetic field lines are going to be increasing. Apply current. Okay, so if current increases, then the inductor resists. Let's see, the inductor will resist the increase. The inductor, so if the current increases, then inductor resists the increase. And if the current decreases, the inductor will resist the decrease. Because as these magnetic field lines get smaller, they will put voltage back into the circuit, which is sometimes why when you flick a switch off, when you have an inductor, you get this arc that appears. So we have this like switch. And so when we turn it off, that back EMF is so high sometimes, like if we instantly turn it off, that it will zap back. And that's when this comes back, and that's the back EMF. It just appears when we turn it off. And so the other thing is what happens in that first instant. So right after we turn on current. Turn on current. How much goes through the inductor? So if we just, instantly turned on the current, how much current will be flowing through and out the other side of the inductor? And the answer to that is 0 for that instant, because if we instantaneously change the current, then the inductor will instantaneously resist. And so the unit for inductors is the H. We call it's Henrys. It's called the Henry. That's the unit. And so what that means is it's the volt per amp. So if we change the current, if the rate of change of current is 1 amp per second, let's see, rate is 1 amp per second. And that will create a back EMF. So anytime we have a change in current, it will have a change in voltage, and that's our back EMF. And so if it was 1 Henry, and if we had 1 amp per second change, then we will have 1 volt of back EMF. And so if we had 2 Henrys, then what we're saying is we'll have 2 volts for every amp per second change in current. Sort of like with a capacitor. A capacitor is the amount of charge per volt. Here we have the amount of volts per change in current. And it's only when it's changing. And so this means that when we have our current applied at its maximum, there's going to be energy stored in the inductor. So energy is stored. And so the energy is stored so the energy in joules is equal to L times I squared divided by 2. And so L is also sort of our Henry. So if we have a 10 Henry inductor, then we'll have an inductance of 10 Henrys. So L is the inductance. And the current is the amount of current applied. So if we have 5 amps, then we would have 25, because we're timesing it by itself, squared. And then we divide it by 2. So that's our amount of joules, because that means that if we were to stop the current, then the magnetic field lines would decrease, and as they decrease, they would put a voltage in which would have this much energy. And so that's sort of a general overview of inductors. All it basically is saying that we need a change in magnetic field, and that will create a current in another loop. And so when these loops are intersecting, that explains why the inductors are in this crisscross shape, because when they have this magnetic field line, then they will all intersect. You don't get that with this type of circuit, where nothing is intersecting anything else. And so it's pretty important to understand this, and hopefully this helps.